give this a bit more thought. Perhaps I need it as well. Anyway, bottom line is that this mapping from L to B is 1-to-1 and it's onto. You may need to give yourself a bit of thought on why is it onto. Maybe do that as homework, right? Okay, if you assume that this mapping from L to B is bijective, it's a correspondence, then given that B is uncountable, therefore L is uncountable, and that's what you're after. Okay, so therefore, because B is uncountable, then L must also be uncountable. Right? So you've got it. You've got it then. So in other words, this set of languages, there's no bijection or no correspondence possible between the set of languages and the set of all Turing machines, because the set of Turing machines is countable, and the set of languages is uncountable, and the set of languages is uncountable because it's isomorphic with the set of B, which is uncountable. Have you followed all that? All right. And that means, therefore, there are some languages, I've said this several times now, that there are some languages that are not recognized by any TM because there are more languages than there are machines, Turing machines. So some languages can't get paired off 1-to-1 with a Turing machine. Some languages have no Turing machine that recognizes them. Okay? Right? Now we're just starting on the big thing. So the halting problem is undecidable. I assume you now know the difference between decidable and recognizable. I'll talk about that quite a few things. All right. So now with all these tools, finally we can go back to Theorem 411. That was on page 176 in your text, which was saying that this language here, A suffix TM, there's a bit of revision, written it down again, which is a set of ordered pairs MW. M is a Turing machine, and that Turing machine accepts the string W. That's the condition that this binary pair is a member of this language. It's a string, right? Because it's the encoding of these two bits of information, two things. The machine, the encoding of the Turing machine, and the string. All right. Now, how do you prove it? Now, I'll just start on it, and I have to repeat this probably next session, next board. Okay. Just broad strategy to start with. We're going to use, once again, proof by contradiction. Okay. We're going to assume that there is a Turing machine. Well, we'll assume this language is decidable. Okay. That, in other words, there is a Turing machine that decides the language. Remember what that means? It means that the members of this language, the Turing machine accepts, and all strings that are not a member of this language, the Turing machine rejects. Right? In other words, in all cases, the Turing machine halts. Okay, and hence halting problem. Because so we're proving by contradiction. So we're assuming the opposite of what we want to show, and the opposite is that there is a Turing machine that can decide this language. Okay, so let's call this Turing machine. Let's call it H for halt, the halter, if you like, and it's a decider, right? For this language. So it would accept this string. It would accept any member of this language. In other words, each of these strings, and it would reject any other string. By definition, it's a decider. Okay. Now, so that means if this gets input to H, then it would, what would it do? It would accept, right? Because, wait a minute, depends on what M and W is. Alright, just a minute. So, if this M accepts this W, therefore this machine accepts this W, therefore this ordered pair is in this language, okay? And since H is a decider for this language, this member of this language has to be accepted by H. So in other words, H accepts this binary pair, this ordered pair, if M accepts W. Okay? Now, if M, let's see what happens. If M does not accept W, then this ordered pair MW is not in this language. I hope you're following all this reasoning. So if M does not accept W, then this ordered pair MW is not in this language. Okay? And therefore this Turing machine H, it should reject this pair. Okay? Because H is a decider. So in other words, H should reject this pair if M rejects W. If that was too fast for you, rewind. Okay. It's getting tougher. Just a sort of side comment, almost interesting psychologically. Like when I was teaching this kind of stuff to my Chinese class, and there were some undergrads in the class who frankly should never have been there. I think it was a strategy mistake. It was probably a financial non-mistake on the part of the dean, because I'm sure he was making quite a little bit of money out of this whole deal, maybe illegally. And he just piled in the students as he could. Anyway, some of these, the dumber ones of the undergrads, by undergrad standards, would come up to me and they'd say, "Oh, Professor, I don't understand. And I'd go through this, I'd try to make it as clear as possible. And whatever I did, they just could not get their minds around the level of abstraction. They just couldn't do it. So there's some kind of threshold needed for them to be able to do that, and they just couldn't do it. So eventually they gave up, I gave up, and they just sort of walked away, and then probably the next day, next week, they'd say, I'm quitting the class, can't cope with it. So an interesting psychological question, what is it about certain mathematical proofs, the level of abstraction or whatever, that makes it impossible for certain brains, the way they're wired up, IQ I guess, that they can't cope with it. Now others, like especially the brighter master students, no problem. They understood it like the first time I stated. I didn't even have to repeat. They'd get it immediately. So you've probably heard the expression "getting your mind around something." Maybe. Well, it's just an analogy, but something like that is going on. The artificial intelligence guy in me dreams one day we will have a mathematical IT, intelligence theory, so we could actually explain this kind of phenomenon. Why is it the dumber ones just never get it, can't get their minds around it, whereas the really bright ones get it first time? It's easy for them. What's the difference? Why the difference? Anyway, well, that's as far as I've got on the board. We'll just continue on next session, next board.